An important process that we didn't talk about yet is precession. Precession is the change in the argument of your center. It's a change in the orientation of the orbit. As we saw, the constancy of the eccentricity vector implies that an orbit around the central mass does not change its orientation. It's a conserved quantity. The argument of the perihelion is always at the same point. So what is causing precession? Turns out that one of the things that causes precession is the fact that a body is not always orbiting a point mass. If the body is not a point mass, you're going to have some extra gravitational terms, some extra forces, and that may lead to precession. So let's see how that arises. How is the potential of ablate bodies? Newton's second theorem says that a spherically symmetric body affects external objects as if all its mass was concentrated in its center. Now, that only applies indeed for spherically symmetric bodies, but planets are not spherically symmetric. You can expand the gravitational potential of a non-spherical planet and find that its gravity is going to be given by a multiple expansion. We call this the J-coefficients. So if you do not have rotation, that's a sphere. Now you have first, second order, third order effects from the multiple expansion. We call the first order effect the J2 coefficient, the second order effect the J4 coefficient, the third order effect the J6 coefficient, and so on. So let's see how this arises. If you have the gravitational potential being the monopole plus a deviation, and now you expanded the deviation in spherical harmonics. Now, because we have azimuthal symmetry, the expression cannot depend on azimuth. That means that all of the S and N coefficients are 0, and the only non-zero coefficient is the one for m equals 0. So only Cn0 is non-zero. So that simplifies the expression. Now, if you define Jn as a negative of Cno, then you can write the deviation in terms of the J coefficients. Now, the shape is going to be given by this Pn here, which are the Laplace polynomials. These are some of the first Laplace polynomials. Where those shapes are coming from. You have here the first, so n equals 0, you only have the Pn is equal to 1, so you only have the monopole. For n equal 2, then you have this oblate sphere, which is the paraboloid. For n equal 4, then you have an x to the 4th power. These are some of the coefficients for the planets measured by spacecraft. As you see, the J2 dominates after the monopole term, and the other coefficients are very small. But how does this lead to precession? Let's write the gravitational potential up to J2. The perturbation is, so the gravitational force is going to be the gradient of this potential. So I have a force that is proportional to r to the 4th power. What is the orbit around the central potential that falls with r to the 4th power? So we have this force. You can write it in terms of the perturbation force. So because of the gradient in theta, cosine theta is z over r, that is going to be a vertical force. But let's ignore that at first and look at what happens with the radial force. If you bring again the Gaussian equations, there is no azimuthal perturbation. And let's ignore for now the vertical perturbation. So you're left with very little. You have a semi-major axis disturbance, an eccentricity disturbance, and disturbance on the argument of perihelion. Notice that the angular momentum is conserved, as you expect for a central force. So let's eliminate the zero terms. And let's give a bar here to this r so that we don't confuse it with the radius of the planet. So the only thing in this r bar is the mass of the planet, the radius of the planet, the radial position, the J2 coefficient, and theta, which is a function of z. None of that changes with the true anomaly. So let's average over an orbit. It turns out that over an orbit, the average of the sign of the true anomaly is equal to 0. The average of the cosine, though, is not equal to 0. You can see that from looking at the orbit. Because of Kepler's second law, the planet spends more time at this side of the orbit than it spends at this side of the orbit. But it spends equal amounts on the upper part of the orbit as it spends on the downside of the orbit. Therefore, the sign here is positive and here is negative is going to average out to 0. But you cannot say that about the cosine, because the cosine is positive on this part of the orbit and is negative on this part of the orbit. And the planet spends more time, or it's slow, on the negative cosine part of the orbit than in the positive part of the orbit. But if we know that the average of sine of the true anomaly is equal to 0, then we can average the equation for semi-major axis and eccentricity. They average out to 0. Turns out that the average of cosine f is equal to minus the eccentricity. So in the orbital plane, you end up with this expression for the evolution of the argument of pericenter. The semi-major axis is constant, the eccentricity is constant, but the orbit is going to change its argument of pericenter because of a non-zero J2. And this is what is shown here. You have an orbit around an oblate body that has a non-zero J2. You start from this orbit here, the red, and slowly, because of J2, you are changing the direction of the argument of pericenter, whereas the semi-major axis and the eccentricity are held constant.